Okay, good morning everybody. So a couple announcements before we start in on class. You guys have an exam on this coming Wednesday. Hopefully you're aware of that. I sent out an email announcement about it. There is a practice exam. It is on Blackboard in the folder that says practice exams. You can tell that it's the practice exam for the second exam because it says practice exam 2. And it's 5 questions, and it's not comprehensive, okay? So the practice exam is not meant to be like your study guide to help you prepare for the exam. It's meant to give you an idea of the sorts of questions that will be asked, the way that they will be asked more specifically, because I have to change that in the at-home, take-home exam format. And also just give you a general barometer for your preparedness. So what I would recommend you to do would be to pull up the practice exam, get out your notes and your textbook or whatever, but do it on your own and see what you can do under the same conditions that you will be taking the exam under. Okay? If you do pretty well, then that's a good indicator that you are well prepared. If you find yourself performing poorly, maybe that's an indicator that you should do a little bit more studying. So I want to give people a little bit of time to try the practice exam before I upload the solution. I have the solution video locked and loaded and ready to go, so I'll upload it probably tomorrow, maybe? Tomorrow sounds good. Does anybody really prefer that I put it up earlier than that? Okay, I'll put up the practice exam solution guide tomorrow. You still have a homework due this week. You also still have a homework due next week. I just want you guys to be aware of that. The way that the content comes in this class, there's not really time for us to take a week off from homework because of the exam, unfortunately. Sorry. On the other hand, I have increased your attempts from 3 to 6, so hopefully you guys find that helpful for when you go and do those homework problems. Any questions? Yes?
Is the exam cumulative or only on the new stuff really?
Okay, so I cover that in the exam preparedness video, which I have on the YouTube channel. It tells you what you should know from each section. I'd recommend that you guys all watch that. It covers sections 2.3 to 4.4, or at least the sections that we covered in between those two things. But exam 1 knowledge is basically implicit in most of these problems. So you should be very familiar with everything we did from exam 1. For example, I might ask you a problem about doing derivatives of exponentials, which might require some of the knowledge from the chapter where we talked about how to find the function of an exponential given points on a graph or something like that. So that's just kind of the nature of math. I'll try to make most of the problems sort of the main content piece of each problem will probably be from 2.3 to 4.4. Good question. Any other questions? All right, like last time, we won't have class on Wednesday. That way you'll have that time to feasibly do the exam if you were busy all of the other 11 hours of the day. Okay, so I want to go back really quickly and talk a little bit more about 4.2, and then we'll get on to 4.3. In particular, I want to expose you to a certain type of problem, which is this type of problem where they give us some information about a function f in terms of its derivatives. And what we're supposed to do is come up with the graph of a function which could satisfy these 4 properties. Okay, so the properties that we want to satisfy are f should have a critical point at x equals 4. They don't specify whether it should be a local min, local max, or neither. F of x has an inflection point at x equals to 8. That means the concavity is changing at x equals 8. The value of f prime is negative to the left of 4 and positive to the right of 4. Okay, so that's kind of telling us, this piece of information goes with this one, right? That's going to tell us whether that's a min or a max. And the value of f double prime is positive to the left of 8 and negative to the right of 8. So give this a shot on your own for a few minutes. See what you can do, and then we'll draw a few graphs and try to figure out which ones could be feasible. Would anybody like a little bit more time to do some drawing? What do we think of this problem? Is it tough? Let's have some thumbs. Thumbs up if you feel like it's pretty easy, thumbs down if you feel like it's pretty tough. Sideways if you think it's somewhere in the middle. Okay, I'm seeing more sideways thumbs than usual, so maybe that indicates that this is a bit harder than normal. I think it's harder than taking a graph and figuring out these kind of pieces of information. That's what we usually do. Okay, so what I'll do now is draw up a couple of graphs and we'll decide together as a class whether we think these graphs agree with these four properties or disagree with any of the properties. Okay, let's start with this one. First of all, I know that x equals 4 and x equals 8 are important points, so I'm going to make sure to mark those on my x-axis. So here's 4 and here's 8. So here's the first graph. We could make it look like this. That's my first graph. So let's take a second to let that sink in. And then I'll ask, do we feel this is a good graph? Feel this is a bad graph? Okay, for those of you who are shaking your heads, saying no, this is a bad graph, could you tell me the color of the property that is being violated, or the color of one of the properties that's being violated, if multiple? Yes?
Green.
Let's see, the green property says f double prime of x is positive to the left of 8 and negative to the right of 8. Which part of that property is being violated?
The negative to the right.
Yes. Very good. F double prime should be negative to the right of 8, meaning that in this green region here, our graph should have negative second derivative, which would tell us that our graph should be concave down in that region. Since our graph is having a U-type shape, as in the letter U in the word up, we know that it's concave up, so that rule has been violated. Any other rules being violated? Kevin?
If the green one's being violated, the yellow one is too, kind of.
Yeah, that's an excellent point. The yellow one's also being violated, right? What does the yellow property say? It says f has an inflection point at x equals 8. That means that the concavity changes at x equals 8. But what we can see here is before we're concave up, and then after we're still concave up. So there is no inflection point at x equals 8. Very good. Okay, what about the other two properties? Red and blue. Do we feel those are being violated? Okay, seeing some heads shaking no, and I agree with them. F prime is negative to the left of 4. What does that mean? That just means that we're going down. Yeah, that's a really bad arrow. We're going down, and then afterwards we're going up. And we also have a critical point at 4 because, well, it's kind of hard to tell, but that is the minimum. Okay, so if you were to be doing this problem on an exam, this would be a good method for checking your work. You know, give it a shot and then go through each property one by one and verify whether or not your graph satisfies those properties. All right, we'll erase that one. Let's try this one. Anybody have a graph that looked kind of like this? All right, well, let's check. Do we think we have a critical point at x equals 4? Okay, heads are shaking yes. For those of you at home, I wish you could see it. Everyone's shaking their head yes. Okay, so yes, we do have a critical point at x equals 4 because visually we can see it's a minimum. Minimums will only occur at critical points. Doesn't mean that every critical point will be a minimum, but if a minimum occurs, it has to happen at a critical point. Necessary but not sufficient condition. That's what they call that. Okay, the value of f prime is negative to the left of 4 and positive to the right of 4. Absolutely right. Because it's a minimum, right? We're going down, and then afterwards we're going up. So these two check out. How about the yellow property? Is the concavity changing at x equals 8? Yes, it is. To the right of x equals 8, we're concave down. To the left of x equals 8, we are concave up. If we're concave up to the left and concave down to the right, is this green property going to be satisfied? Yes, it is, right? Because concave up means f double prime is positive. That means concave up. F double prime negative means concave down. Okay, great. So, my recommendation with a problem like this would be to start by digesting these rules individually and build your way up. Okay, so the first thing I might do is look at the red and the blue rule and say, okay, between these two things, we can kind of describe what's going on at the point x equals 4. Namely, it should be a minimum, right? Then we can take into account these other two rules. We can say, okay, what's going on at x equals 8? It's an inflection point. Well, if it's an inflection point, let's decide what the concavity is going to be on each side, right? So if you know you have a minimum and you're concave up, that kind of gives you this whole first part. And then you know that the concavity should change at x equals 8, but f prime should still be positive. So we should be concave down, but going up. Okay, so here's how I would like to describe these things. What I would do is I would take these rules, and I would, for each interval, describe what's happening with the concavity and the first derivative, namely decreasing or increasing. In the first part, we have f prime less than 0, f double prime greater than 0. In the second part, we should have f prime greater than 0 and f double prime greater than 0. In the last part, we should have f prime greater than 0 and f double prime less than 0. So once you have this green line at the bottom, that's a good way to start. And then you can start to kind of draw, well, what does it look like for a function to be decreasing and concave up? It's exactly what it looks like in that first region. Okay, your graph could have also looked different than this. Could have maybe looked like this or something like that. Or it could have been bent in a little bit of a way or something like that. So if your graph doesn't look exactly like mine, don't worry about it, but do check whether your graph satisfies these properties. Okay, so that's all I want to say about that. Well, are there any questions about this problem? All right, if not, then we will move on to 4.3. So what are we doing here? We're going to talk about global minimums and global maximums. So far we've described everything as a local minimum or a local maximum. What local and global mean in math is the same as what local and global mean in sports. Okay? You ever heard of like a local champion? Like if you're the state, if you win state for your like high school sports team or whatever, then you're the best team in your local area, being your state, right? But if you're the global champion, then you're better than everybody else everywhere, right? The same thing is going to apply to our local maxes and our global maxes. A local max might be some place where the graph hits a high point, but it's not the high point of the entire graph. Okay? That's what we mean when we say a local max. When we talk about the global max, we say, let's take a look at all of the local maxes and see which one's the best. It's just like after you go to state, maybe you go to nationals. I don't know. I'm not a sports person. I presume that's what happens. Okay, so let's go ahead and do this first problem here. What we're supposed to do is draw a circle around every local maximum, and we'll do that with purple. Well, local maximums are where we're going to hit a peak. It's going to be this guy, this guy, this guy. So local maximum just means hit a high point. And a local minimum just means hit a low point. Notice I'm using the word a here. Hit a high point, a low point. So our low points are going to be these two low points. Now for part B, if we want to draw a square around every global maximum and global minimum, well, those aren't going to be just a high point. They are going to be the points where we hit the high point. Hit the low point. Okay, I think this is fairly self-explanatory. Our square is going to go above the highest point. That's our Mount Everest. And then the square that's green is going to go around our lowest point. That's like our Marianas Trench. Questions about this graphical definition of a global maximum, global minimum? Okay, there's something I want to talk about, which is when we talk about a global maximum or a global minimum for our class, we are going to refer to these things as existing in a given interval. Okay? So, I'm considering this interval from A to be my globe, and I want to find the maximum of the function on my globe, globally. Okay, so let me draw what I mean. Here's a function. And based on our previous definition of what a global maximum is and a global minimum is, we'd expect them to occur at these 2 points, right? Okay, now what I'm saying is we can only consider the global minimum and the global maximum if we specify where we are talking about. Okay, so I might say, or ask on an exam, what is the global maximum of f of x on the interval 4, 9. Okay, so this is the interval 4, 9. 4, 9 is just this section of x values between 4 and 9. So the global maximum of f of x on the interval 4, 9 is going to occur here. Okay? So if I ask you for the global maximum, you better ask me on what interval. Otherwise, I'm not being fair to you, okay? This is how we're going to do global max. Yes?
If you don't say it, should we just assume that you mean like the whole graph?
I'll always say. Unless there's a homework problem that's... I can't remember if I assigned a homework problem that's like that. Yeah, that's pretty safe. But I should specify every time, and if I don't, you can be mad at me. And just send me an email and I'll get it fixed, okay? All right. So that's what we mean when we're talking about a global max and a global min. Okay, so now we're going to talk about when a global max or a global min is going to occur, okay? So to do that, we're going to go back up, unless there's any questions about this stipulation that I added to the definition of global mins and maxes. Okay. Okay, so we're supposed to find all the local maxima and local minima of this function g of x equals x cubed minus 9x squared minus 48x plus 52. So this is a problem from last time. I'm going to go through it sort of quick, and then we're going to talk about finding the global maximum on some interval, okay? So first we got to find these local maxes and local mins. And the game that we're going to play after that is, okay, which local max is the global max, okay? So first of all, I need to find g prime of x. And it's going to be equal to 3x squared minus 18x minus 48. Power roll 3 times. Okay, and well, if I just want to find the local maxes and local mins of this function, I should just find the critical points. And the critical points are just going to occur when this is equal to 0, right? When it's equal to 0, or... what's the other place that a critical point could occur? Yeah, if the derivative does not exist. Why didn't I write down that part of this?
It's a polynomial.
Very good. It's a polynomial. In polynomials, the derivative always exists. We don't need to worry about the DNE condition. So we're just going to worry about this equal to 0. Okay, so let's solve this. This is just a quadratic. We can go back to our algebra 2 roots. I'm going to divide both sides by 3. And I'll get x squared minus 6x minus 16 is equal to 0. Now when I factor this, I think we did this one the other day, didn't we? This is going to be x minus 8 and x plus 2, I think. So that's going to tell us that our critical points are going to be at x equals 8 and x equals 2. And as usual, I didn't leave myself enough space. Sorry? Thank you. Yeah, it should be negative 2. I'm always missing negatives. Okay, so now let's classify them as local max and local min. Well, let's have a vote. Raise your hand if you want to use the second derivative test. Raise your hand if you want to use the first derivative test. Okay, we had about 3 votes for the second derivative test and 0 votes for the first derivative test, so we're going with the second derivative. Let's do it. G double prime of x, that's going to be equal to, what, 6x minus 18. Sweet. So, now how do I proceed? I'm using a second derivative test. What should I do now?
You should plug in the critical points.
Yes, with the second derivative, we can just plug in the critical points straight into the second derivative and see what pops out. So let's try 8. We'll get g double prime of 8 is equal to 48 minus 18. Pretty sure that's bigger than 0. How about g double prime of negative 2? Hang on a second, something's wrong here. G double prime of negative 2, this is going to give us negative, oh yeah, okay, there we go, negative 12 minus 18. We're good. It's less than 0. Phew. All right. So, which one's a local max?
Wouldn't it be 8?
So 8, we've got g double prime of 8 is larger than 0. Does that mean we're concave up or concave down?
Concave up, so that'd be a minimum.
Yeah, this means concave up, so it's going to be a minimum. The other one, we're concave down, that one's going to be a maximum. Okay, probably 90% of calculus students make this mistake at least once. Better to make it in class than on the exam. So, we have this minimum here. It's going to occur when the second derivative is larger than 0. Okay, it's a little bit counterintuitive because we think big number, larger than 0, maximum. That's what goes off in my head anyways. But we have to be careful. Okay, we have to be careful. I recommend you draw these little U's or N's to make sense of it. So we're going to have a minimum, or a local minimum, at x equals 8, and we're going to have a local max at x equals negative 2. Okay, so now we're supposed to use our graphing calculator to graph the function g from problem 2 on the interval from negative 5 to 14. Okay, so what I did was I did this on Wolfram Alpha, and here's what it looks like. So our interval from negative 5 is like right here, up to 14 is here. Okay, so the interval of x values that we're talking about here is, oh, come on. You didn't want to straighten out? Be good. Straighten out. Okay, it's this interval of x values. So we want to find where is the high point and where is the low point for x values which are in this interval. Okay? So let's parse the information that we have already. We already know we have a local min at x equals 8. And we know that x equals negative 2 was a local max. So that makes sense. Here's x equals negative 2, we've got a max, and here's x equals positive 8, we've got a min. Okay, so what I'm going to describe now is the process for finding the global maximum. Okay, so let's first answer this question here. What does it say? Are the local maximum and minimum that you found, so let's decide first. Let's decide where is the global maximum of our function on the interval -5 to 14?
-2.
The global maximum? Let me rephrase my question. Is there a point on the graph with x values in this purple line that's higher than the graph at the value x equals -2?
At 15.
Yeah, well, I guess I kind of drew it wrong. It should have been at 14. Sorry. There's 14. Yeah, I think this point right here looks like it's a bit higher than this one over here. Okay? So if I was going to describe graphically where the global max is, I would say global max at x equals 14. How about the global min? What do we think? Where's the low point in this interval? Yeah, Ashlyn? It is still going to be at 8. We have a global min at, we'll go back to purple for that, x equals 8. So our local minimum turned out to be a global minimum. However, our local max didn't quite cut it to be the global max. Okay? So what is this saying here? This is kind of saying that local mins and local maxes are candidates for the global max. Okay? Critical points are candidates to be a local min or a local max, and local mins and local maxes are candidates to be the global min and the global max. It's like a bracket. Okay, you got to make it through both tiers. Okay, so that's what's going on here. So let's see if we answered the question. The question was, are the local maximum and local minimum you found in the previous problem also the global max and the global min? We said no for the global max, but yes for the global min. So why or why not? Well, the reason why is the graph is higher at x equals 14 than it is at x equals -2. Okay, so that's the takeaway message here. So we already did this. Okay, so based on our observations in problem 3, we want to complete this list of places where you might hope to find the global maximum and global minimum of a function on the interval a comma b. Say it in generality. So we have some interval. We know that the global max might occur at a point where f prime is equal to 0. It might occur at a point where f prime is undefined. How can we expand our understanding of the critical point theory to include this case here, where we wound up having a global max that wasn't one of those two things? Where else might we hope to find a global max? Yes?
Like at the end of the interval.
Yeah, at the end points of our interval. We also call those boundary points. They're the boundary of our domain. They mark where it starts and ends. Okay, so that's how we're going to expand this. So the 3, I'm going to put the points x equals A or x equals B. Okay, so what I'm now going to do is give you a comprehensive guide to using critical point theory to find global maxes and global mins on an interval. Before I give you the lowdown on that, are there any questions about the problem we just did or about how we're expanding these list of candidates to include the endpoints? Okay, sweet. We made it through the trick question. So let's get on to an actual, that's too far down. Let me cut this stuff. Move that down there. Okay, so here's where I'm going to write our how to find global max and min of the function f of x on the interval a comma b. Step 1, take derivative of f of x. That's going to be our first step. Why do we want to take the derivative of f of x when we're trying to find the global max and min? Yeah?
To find the local maximum.
Yeah, to find the critical points, right? You want to find the critical points. Well, the critical points occur when f prime is equal to 0 or doesn't exist. Okay, so take the derivative of f of x. Second step, find critical points. X equals p, where either f prime of p equals 0 or f prime of p doesn't exist. Okay, so once we have all the critical points, we're going to do step 3. Make a table with all global max min candidates and the value of f of x at each candidate value. So what is that going to look like? We're going to make a table. Okay, so for example, what if our critical points were x equals p1, x equals p2, and x equals p3? Okay, so we found 3 critical points, something like that. Then what's going to go in our table is going to be all of the candidates for our global min and max. So we'll have P1, P2, P3, the value at those points, f of P1, f of P2, f of P3. What else should go in my table? I put in the critical points. Where else might we find a local or a global min or max? Alice?
The boundary points.
Yeah, the boundary points. The boundary points are the boundary points of our interval. A and B. We should put those in here as well. So I'm going to put A here and B here. F of B. So this is the strategy, okay? Now what? Step 4. Find the biggest number on the right side. The corresponding point x comma f of x is the global max. So what are we saying here? We say, let's find the value of f at all of the critical points and all of the boundary points, and just look for where the function is highest. So we look for the biggest number among these guys highlighted in green. Whichever one is the biggest number is going to be the biggest, highest point of our graph. And we know that the global max has to occur at one of these candidates. It has to occur at a critical point or at a boundary point. So if we find the biggest value among all critical points and boundary points, that will be our global maximum. Likewise, smallest number on the right-hand side will correspond to the global min. So that is how we find the global max or the global min of f of x on an interval. So we want to know who's the best high school wrestler in the country. What do? First, we hold our state championships, right? Once we know all of the local maxes, aka the local champions, then we pit all of them against one another in this table, and we see which one is the best. That's what we're doing here. We're also adding in these endpoints. I'm not sure if there's a wrestling analogy for endpoints. Maybe these are, I don't know, the champions from last year or something. Okay. So are there any questions on this sort of algorithm that I've proposed for finding global mins and maxes? All right, man, I got 2 minutes left. Not sure I have time to do this whole problem. Tell you what, I'll get it started and then we'll stop. Okay, so if we have this function e of t equals 0.25t, hang on, do I really want to do this? I'm not going to do this. Yeah, I can't give a good explanation of this problem in 1 minute. So we'll be done for today. I have office hours today from 11 to 1. Don't forget, you have an exam next week. I recommend you study over the weekend and come to office hours on today, and I'll also have office hours on Monday. There are SI sessions. There are Math Tutoring Center people who will help you constantly all the time for free. If you are worried about like studying or that sort of thing, just let me know and I'll help you, okay? You're going to Atlanta, you said? Okay.
Is there any way that I can schedule an appointment with you on Sunday?
Sunday.
Or even Monday? I have a class at noon on Monday, so I wouldn't be able to come to your office hours. But
Yeah, sure. Can you send me an email and I'll email you back?
Yep.
Are your office hours in Blackboard today?
Yeah, they are. So the link is on Blackboard. You just click the one that says Friday office hours. It's technically in the MTC room or whatever.
Okay.
But yeah.
So there's a folder in Blackboard that's like your office hours.
Yeah, here.